for it, and I'll try to, there we go.
I was gonna say, I recorded it to the cloud. Hopefully that's the right place. I can stop and record it. Yep, right. Okay, well, hi everyone, and thank you for coming to the webinar today, and apologies again for the confusion with the time. So my name is Heather Brown, and I'm one of the conveners for the special interest group on teaching health economics, in case you're not members and are interested in joining. And this is our webinar for this year. So we have two fabulous speakers with us. We have Robert Smith, who works with Dark Peak Analytics and also is affiliated with the University of Sheffield, who specializes in methods from data science for health economic evaluation. He has a PhD in public health economics, and Robert will be speaking first. And then we have Sanne, who is an epidemiologist and is currently undertaking a PhD in health service research from the University of Twente in the Netherlands. And Sanne will be going second. So how this is going to work is we're going to have each of the speakers present for approximately 20 minutes, and we might have 5 minutes for questions specifically related to the speaker in between each presentation, and then we'll have a bit of time at the end for general discussions. So now over to you, Robert.
Thank you, Heather. Hopefully you can hear me all right, and I'll show my screen and we can check that you can see the screen. So hopefully you can see the slides.
Yes.
Brilliant. Okay, thank you everyone for attending and for the invitation. It's great to be here today. So I'm going to start by talking about generative AI for health economic evaluation in general, and then look a little bit about some work we've been working on in building software and tools to help review models. So I guess the first thing to say is that there's very limited peer-reviewed literature out there on generative AI for health economics. There's some kind of early papers that are essentially looking at, what are the opportunities, what are the challenges, what are the policy considerations around this. And there's a really nice paper by Florence et al. That I'd recommend having a look at. Kind of gives an idea of the landscape, where things are, and some kind of signposts to some early works. Looking more specifically at actual published papers and methods, there's a nice paper by Reason et al. 2024 for some work done with BMS, looking at using AI, so generative AI, to automate some health economic models in the R programming language. And they provide a case study of how that's done, and I'll talk a little bit about that later. I'm sure we'll go to questions about those kind of methods. And then what I'll kind of discuss a bit today and talk about a bit today, for those that are from a health economics background, is an R package that we've been working on to help improve quality assurance of models. So from a teaching perspective, this might be useful for those that are trying to kind of learn to understand a model that's been provided to them, say a teaching model or a model that they're reviewing for some reason. But it would also be useful when building your own model to try and understand how your model could fit together correctly, and to do quality assurance as you're building your model. And so we've written a paper on that package as well, which is currently in press, but we've got a preprint that's ready for download, and I can share the link after the presentation. So in terms of the background and motivation for this this piece of work, so generally speaking, when we're kind of asking somebody to review a model, or even when we come back to our model after say 6 months, the conversation might look a bit like this, and somebody would say, can you help review this, or can you review this piece of work, or you'll get asked by your line manager or your boss to review some work, and you'll open it up and it will be something like this, and it will just be a lot of code, and even a very well constructed model is still going to be a huge amount of code to kind of debug and try and understand how that all fits together. And so then you might feel a little bit like this. And that's often the experience of people reviewing the models or coming back to models later on, whether that be in Excel or R or Python or whatever programming language you're using. It's very kind of difficult to understand how they fit together. And so we developed this this R package called AssertHE, with the idea being that we'd provide a set of tools that made it easier to verify models and validate models that had been created, and also to check as you are developing a model to check that you're constructing it correctly and haven't got any obvious kind of bugs and errors within the model. And so what this outputs is a visual representation of a network of algorithms. So for those that aren't health economic modelers, the models that get constructed will typically be a series of equations and algorithms that are either nested or sequential. And so you might have one calculation that's being done that calculates the costs associated with some treatment, or defines transitions between different health states, or calculates health state utility, and those different equations and calculations will be done kind of sequentially, but also will be nested inside one another. So you can end up with some quite complicated networks of algorithms. And so trying to understand how that all fits together is very complicated. And so when we open up a model and look at a model, we want to know, has this model been tested in a coherent way? Does it make sense? Can I understand how this model has been constructed and how this problem has been kind of conceptualized? And so having a visual representation of that can be really useful. So what's up on the screen is an incredibly simple teaching model that we used as a kind of case study to help build the software. But I'll go through later some kind of production-ready models that have been used by NICE, for example. And so what can you see? So when you click on one of these nodes, you can then see the name of the algorithm or the function, where that function is located within the code base, and where any corresponding tests are located, and also the code coverage associated with those tests. So if someone's written some very well constructed code, then you might expect that they have tests of that code to ensure that runs correctly, and coverage might be really high. Whereas if they've not written any tests on that code to make sure that it's doing what they'd anticipate, then you might get very low or no coverage. So what we've done is color in anything with above 80% coverage green, and anything with below 20% coverage red, and yellow between those two figures. A nice thing about the tool is that as you're starting to conceptualize your model, you can add in your own functions within the tool and kind of show where they would sit. And so we can see this being particularly useful for teaching in a kind of education setting, but also for teaching junior colleagues when building models, because you can, rather than just say, okay, so we want to build in or adapt this algorithm to do X, Y, and Z, you can click and show how these different functions that you're proposing would all fit together given the current modeling structure. And this is all completely interactive and can be saved and sent to other people. So then so far it's essentially been a kind of an exercise in computer science and network analysis of algorithms that are constructed in a programming language. The kind of AI or generative AI bit of this is in once we've broken down this problem. So you have a model and you're trying to understand how that model works. Once we've broken down the problem into lots of small functions and algorithms, we can then pass those to a large language model and get them to summarize each function. So if we were to try and do that for the entire model, we'd be passing through way too much code, way too much information, way too much complexity to the model, or to the large language model, and it wouldn't be able to cope. So if we just gave it an entire R model with 2,000, 3,000 lines of code and pass that through to a large language model, it would really struggle. But if we pass through a single function with 20 lines of code, large language models are surprisingly good at summarizing and providing a kind of clear layperson representation of what that function is doing. So that's what we go about doing. So within this tool, essentially we allow you to click on any of the functions from the model and click this robot button, which generates a large language model summary of what that function is doing. And so what that does is extracts data about that function from the documentation. So it takes the arguments that pass to the function, the body of the function, and the outputs, and it stores all that information as data. It then creates a prompt and feeds that data into a template that we pre-created, essentially to say, we want you to act as a reviewer and provide a summary of this function, and then the data is inserted into this template prompt, and that prompt is sent to a GPT. So for those of you who are familiar with ChatGPT, will be familiar with interacting with a large language model. You type in some text, and the large language model responds. Now that's great if you're a human, but obviously if you want to interact with this from a machine as a computer, you generally want to be working with what's called APIs, and essentially that allows your machine to send the same types of queries that you might type to the large language model online. And so now we have a user interface that allows the user to click and to send this request to the API from OpenAI and get back a summary. So you could achieve a very similar thing by copying and pasting, going into the documentation for the function, copying and pasting all the right bits, pasting that into Word, getting a really nice prompt, and then pasting that into ChatGPT would give you a similar result. But here, obviously, it's just one click. It's much simpler when you're trying to navigate a model. And so we then receive the response, reformat the text, and then show that text in the modal. So this is what that ends up looking like. So say we'd clicked on the create Markov trace function. We weren't quite sure what that function does, why that's there. We can then click on it. It sends the request to the API with the prompt pre-created, and then returns you 2 paragraphs about what that function does. And so we've tested this with a few different case studies. So this is a CDX2 CEA model, so biomarker testing cost effectiveness model that was built by colleagues from Stanford, and we've tested it on that model. It seemed to work fine. So we get this network, and we can play around and understand how the different functions fit together and generate this AI summary for a function. We've also tested it on the University of Sheffield diabetes model. Again, that allowed us to understand how that network of functions fit together, much bigger model. And the nice renal cell carcinoma model, which is absolutely enormous. And so having the ability to see how that model fit together was really useful for those that were working on it and adapting it, and being able to summarize any of the functions, again, really useful. So I've got if I pull this in, so we can actually show what this looks like. So I took a short video of what this was. So you can see here, we can go to any of the functions. We can zoom in. We can click on that function. We can click for review. We wait, it sends off the request, and then we get our summary for that function, which is obviously useful for someone who's completely new to the model. So in terms of next steps, this software is completely open source, so you can see it at the link below on the bottom of the slide there. We're looking at testing the software in as many models as we can, so I think we're up to about 10 to 12 models now, and people have been very kind in testing it on internal models, so things that are not even open source, and suggest improvements. So some people have submitted pull requests to GitHub, which is great, and we're keen to expand the testing functionality. One of the things that we're looking at doing is taking our teaching materials. So we as a company and as an organization run a lot of training on the use of R for building health economic models. That's a big part of what we do. And so we have a huge amount of training content. So we're trying to work through retrieval-based methods to try and kind of augment those prompts to improve them. Yeah, so there'll be a publication shortly on this topic, and we'll be able to disseminate that when we can, but there is a preprint available at the link in the slides. Yeah, so I suppose that's just a sort of narrowed down very quickly into a general focus on reviewing models, but of course there's a much kind of broader perspective around the use of these large language models and generative AI in general on health economics. And so my experience sort of overall is that generally generative AI is much better at summarizing, so dumbing down, than really kind of novel problem solving. So if you were to take something that's very complicated and ask for it to explain it in a kind of simpler way, it's very good at that. Very good at, for example, editing very complex scientific papers and describing them in the language of, say, a 10-year-old. It's incredibly good at that. Coming up with a novel solution to a problem, it's not quite so good. They will make things up with confidence. So the task of the reviewer and the human is still very much needs to be in the loop at the moment. In the future, we don't know, but at the moment, you get a lot of hallucinations and things that unfortunately you have to kind of be an expert to know that they're wrong, which is very dangerous. Volume matters a lot, so they're very good at small tasks. So it's kind of like having a large number of grad students who are quite good at one small thing. So they can't put the whole task together often. And there's an increasing role in recent publications on kind of essentially stitching together prompts to achieve a broader task, but that still requires a lot of human interaction. So just asking generative AI, large language model, can you build my model, at the moment is not feasible from the outset. It just struggles with the nuance of complex series of tasks that are kind of sequential and nested. But it's very good at doing small tasks. So it's kind of splitting problems down into very small tasks and then assigning them to AI systems. Carefully written prompts are crucial. So obviously, if you provide it with garbage, then you get garbage back. And the kind of earliest use case that we've been seeing, and I think pretty much everybody's been experiencing to some degree, is just this replacement for human sort of Googling and looking stuff up on Stack Overflow. I think very huge numbers of people are working with things like ChatGPT on a daily basis, to the extent that we're kind of already using it within our systems. It's just that it's a human who's taking the code from ChatGPT and copy pasting it back into Visual Studio or RStudio or whatever you're working with. So there's probably the next step to kind of gradually reduce the role of the human in that interaction. That being said, there's a huge amount of potential. So we are looking at much more efficient model builds. So rather than spending a week having to code something up, being kind of augmented, human augmentation with GPTs might speed that up to take a day, which then frees up a lot more time for focusing on more interesting things. So methods development, really understanding and conceptualizing the problem, which is a kind of a huge thing if we're wasting a lot of time focusing on the code and on the model build, rather than actually thinking about the big picture. Like, why are we building this model in this way? What are the real kind of drivers for stakeholders? That kind of things. And there's a lot of roles with a big role that it could have for doing things like double coding, reviewing, trying to identify bugs and errors. So there's a few papers published recently highlighting the sheer number of errors that we've seen in recent years in health economic models. So I think having a large role in even just identifying those errors for commissioning decisions worth millions of pounds would be good. And then hopefully having some role in making these models more transparent. So the example that I've given on with our work is obviously being able to summarize these functions that for a layperson, so for a person who's not well versed in programming, they would never be able to understand what that function is doing. And so having an interface like this where someone who's not necessarily a health economist or a programmer can look and understand how the model all fits together and see that is much more transparent. And finally, I think freeing up the time again should lead to a bit more cross-pollination of ideas with other disciplines, and we might see this with if the amount of time it takes to really understand a topic reduce significantly, we might get a lot more ideas from other areas kind of feed into health economics and health economic evaluation, and that's probably one for another whole another talk. There are quite a few challenges though, so there's a danger for open source in general. So if nobody really gets any attribution for their work, because essentially things are getting kind of fed into large language models and then reported back by the large language model, where is the incentive for thought leadership and for publishing? So currently, you might use some method, some algorithm that somebody's created and attribute them. And as much as we would like to say we go to work for the benefit of humanity, there's a certain amount of ego and career progression that goes with that. And so if we're using these large language models and they are just giving us the answers, but based upon published open source code and literature, but with no attribution, then where's the incentive to come up with novel new ideas and to publish them? So there's a bit of a danger there. Obviously, there's the hallucinations and making things up with confidence issue that a lot of people have talked about. There's also another issue of simple tasks like reviewing functions or writing specific small bits of code are done by Gen AI. How do people learn and develop? So at the moment, it's kind of fine because we've got some experienced programmers who can use generative AI to test their work and to kind of speed themselves up. But actually, if nobody's ever learning the initial code base and language, then how do people get to that stage? So when the current 30, 40-year-olds retire, will the generation in 2 generations' time actually really ever get hands-on with the code, or will they just be copy pasting from or allowing GitHub Copilot to write things for them? So this could be a real problem. And then finally, how do we keep the human in the loop? And do we really need to keep the human in the loop? So at the moment, there's a danger that we kind of go from essentially a human writing a series of bullet points that creates a model to then another human receiving a model and asking an AI system to convert that model into a series of bullet points. And so is there really ever a human in that loop? And at what stage do we accept that these systems are good enough? And that's probably a theme that we'll keep coming back to. And finally, will we all be out of work? So are we going to all become Luddites because we're concerned about AI? And I'm somewhat optimistic about this and think things will be fine. And there's always been issues in the past and concerns in the past, but I think it will replace a lot of work that currently is probably the least enjoyable parts of our jobs, and hopefully not replace the most enjoyable bits. So we'll see. And finally, just to say, so throughout, I've discussed working with R, and this came up at another talk recently about whether the use or the development of these tools, so generative AI tools, will cause a shift away from spreadsheet software towards programming languages. And my opinion is that it will, because it's just so much better suited for a script-based solution, so for a programming language, than trying to feed something into a GPT to then output to an Excel file, which just sounds like an absolute nightmare. It's not something I've done. I've only ever worked with R, with generative AI, not Excel. But I think it will kind of cause a shift towards programming languages like R or Python. And so we're kind of trying to prepare for that by making courses available for people so that people can upskill in those programming languages so that then hopefully we can make more models open source and improve these tools, but also so that people kind of understand what's going on. Because if we're developing software and tools to kind of spit out our models from GPTs, then it's really important that lots of people understand what those models are doing and how those models are working. So that's my kind of pitch. And this is my quick comparison to for writing or using a GPT to output an Excel model. It's kind of, I was trying to come up with an analogy in a discussion the other day, and the best example I could think of was having kind of a humanoid robot drive a horse-drawn carriage. It doesn't make any sense to use something that's incredibly advanced to spit out a bit of spreadsheet output when when the obvious thing is to be kind of having that middle ground of writing a series of functions and outputs in R that the user can really understand. So yeah, that's it from me. I don't know if we've probably got time for questions, hopefully.
Yeah. Yep, sorry, I'm just trying to turn my camera on. Does anyone have any questions at this moment for Robert? If so, I don't know, if you can raise your hand, that might be the easiest. I think to go to, I'm just looking, React and raise hand. So it should be on the bottom of your screen. Well, whilst we're waiting for people, I'll ask a quick question. So you touched upon a bit about how this could be used in teaching. Can you go into a bit more detail of how you think this might be applicable for people teaching a health economics module?
Yeah, so I guess the main thing is really understanding how the model all fits together. So at the moment, we think of a series of steps, like the early conceptualization stage. Typically, you'd get taught, and I mean, yeah, correct me if I'm wrong, that you'd want to conceptualize your model, really understand the decision problem. And then there's this step where you're essentially taking a schematic and transferring that over to a mathematical model or a model that's been programmed in some way, either into a spreadsheet or a script. And so what's quite nice is to be able to have a summary back into the conceptual model to say, does this model actually represent this conceptualization? And to be able to see how does this code all fit together. Whereas at the moment, what we essentially do is, for a lot of people, is basically just review the conceptual framework and model, review the parameter inputs, and then just kind of hope that the model is right. And that maybe is a bit dismissive, but I think for a lot of people reviewing models, that is essentially what ends up happening, because it is very, very hard to really go through the nuts and bolts of every line of code or every cell, and it's very laborious and boring. So I think there's a big value add from Gen AI in that space, and that's the same for obviously for teaching, because if rather than saying here's 10,000 lines of code, you can stand up in front of a room of 30 and say, okay, so here's 10,000 lines of code, but actually here's how all of this fits together in a diagrammatic fashion, and here you can click here and then summarize this function or this part of the model and get a kind of a layperson summary back, then hopefully that's useful.
Great, excellent. Thanks for that. So someone put in the chat if you could share the link for the GitHub codebook.
Yeah, I can share the link for the. Do they mean the open source software, or the course book is our kind of teaching course book from our courses, but the code base for the software is open source. So I can share the links for
Okay, yeah, no, that would be helpful. Does anyone else have any questions at the time? Because we'll also come back at the end if there's a few minutes. See, I don't see anyone raising their hands. Well, thank you very much, Robert. And now we'll move on to Sanne.
Yes. So if you please could indicate if everything's well visible for you.
Yep,
And you
can
hear
see
me
it
well?
all.
Yeah. Okay. Nice. Okay, so first of all, thanks for the invitation. I was involved in some studies on the evaluation and implementation of AI in systematic reviewing. So from that experience, I will present our insights. And my presentation title already gives away a bit of my enthusiasm about implementing AI into systematic reviews. But I will also discuss how we can remain critical towards its use for the sake of our research methodology. So first I will illustrate the problem. A colleague of mine, Martijn Oudewolgerink, started to perform a systematic review and health economic evaluation studies of early detection strategies for cardiovascular disease. And up to 2021, his search query would have led to 6,500 publications when only searched for in the PubMed database. A very common strategy is narrowing down the search to, for example, look only for the most recent studies. But still, this is a lot of work to screen through. But nevertheless, Martijn did so. And he screened through a pile of almost 5,000 studies to identify 50 relevant articles. This is not quite labor intensive, but also quite error prone. An American study showed that in classic systematic reviews, the human error rate based on decisions in the title and abstract screening phase is about 10 to 11%. So his decisions were checked by a second reviewer, but by the time his review got published, Martijn grew a beard. But he is still smiling, although he admitted to me that this was not the most spectacular research to conduct throughout his PhD. So what if AI could speed things up with regard to the literature selection process? So researchers from Utrecht University, also from the Netherlands, thought of an AI guide literature selection tool to conduct systematic reviews in a more efficient manner while maintaining the quality. So in short, the tool must not miss relevant papers, but these papers should be identified faster than they would when manual screening would be performed. They managed to do so and came up with a tool called AS Review. And this is also the tool that I will discuss in my presentation. I refer to their website for lots of literature about this tool. The coming 10 to 15 minutes will be divided into 3 parts. So in the first part, I will introduce how AS Review is used in practice, how it works. And after that, I will discuss the tool's accuracy and how to implement it. So to grasp what we are talking about, first, it is important to understand how AS Review works without going too much into specific technicalities. But onto the tool itself. Imagine you have completed your search query and have retrieved a bunch of papers which you have to screen through. And this bunch of papers is this pink pool of unlabeled items. So you have to start off a loop, and you do so by labeling some papers. So you label some, give the model, in fact, an example of a relevant paper and an example or two of irrelevant papers. Using that knowledge, the model is trained, and from this pool, it selects the article and shows it to you that the model estimates to be most relevant to you. And as a researcher, you then assess whether that specific item that is shown to you is indeed relevant or is not. So if it is relevant, so in this case it is relevant, it's added to the data that is labeled. And then again, the model is trained again, in fact, and bases its new decision on the labeled data until that point. So again, you get the most relevant estimated item presented to you, and you take another decision, maybe irrelevant. Again, the model is trained, shows a new highest ranked paper to you, and again, you make a decision. And this loop is going on and on and on until you decide to end it. And then you would proceed to your full text screening using the data, so the items, the papers that you have labeled relevant. So generally speaking, the more labeled data, the better the algorithm is at estimating what is relevant to you and what is not. So this loop, and yeah, I said this loop is going on until you end it. So about when to end it, I will discuss that later in this presentation. But important to know for now is that the machine learning algorithm does not make any choices itself regarding in or exclusion. You do that yourself as a researcher. So this approach seems to make sense, and the developers of the tool have shown that the screening process can be accelerated. But we are also, of course, curious to its accuracy. So I was involved in a simulation study evaluating the accuracy of AssertHE. Would it have been used for the systematic review of my colleague Martijn, which I referred to earlier? So the manual screening process included almost 5,000 abstracts to screen through. Only 134 articles or abstracts were deemed relevant for full text screening, and eventually 50 articles were included. So related to the loop that I just explained, this for almost 5,000 abstracts relate to this unlabeled pool of items. And then given the decisions, so given the labels during the screening, we eventually end up with 50 articles for data extraction that are included. And this way, this simulation study mimics the loop that was taken were this systematic review actually being conducted using AssertHE. So 1,000 simulation rounds were run with varying numbers of prior knowledge. So these are the numbers of papers that are labeled before the algorithm is trained for the first time. And what we see that is regardless of how many articles are labeled prior to starting the loop, so whether that's 0 prior knowledge, there's 1 relevant and 1 irrelevant paper, or 5 relevant or 5 irrelevant papers, regardless of the amount of prior knowledge, we see that actually less than 8% of those 5,000 articles need to be seen by the human reviewer in order to identify all 50 articles that are included in the data extraction phase. So it does tell us that it's able to perform accurate and efficient, but it does not tell us anything about when to end the loop, so how to actually use it. So being a researcher in this loop, and not knowing when exactly all relevant articles are identified, it's then quite helpful for you to have some guidance on when to stop your screening. Otherwise, you go on and on until you have eventually screened all 5,000 articles, and that's not what we desire. So we also calculated what proportion of our abstracts would have needed to be screened using different stopping rules, maintaining 100% accuracy. And you can see from this plot is that when you would stop after a consecutive number of irrelevant papers presented to you by the algorithm, varying from 50 to 200, approximately 10 to 20% of the dataset would really be needed to be screened. So, and the upper limit of the black lines represents the worst simulation round out of the 1,000 simulations. So using the most conservative stopping rule, namely ending the loop after 200 consecutive irrelevant abstracts presented to you by the algorithm, and looking at the worst case simulation round, even then, 30 to 33% of the abstracts needed screening, eventually saving 2/3 of your time. So I think it's safe to conclude that this AI tool does what we desire, but we can highly speed up the literature selection process without losing accuracy. So that's nice to know. But now let's discuss how we can make use of this AI tool in a responsible way regarding our research methodology. I worked on a systematic review myself, for which I have applied AssertHE. And what I mainly came across myself was that there are quite some choices you have to make, which would all have their implications for the AI-aided screening loop and consequently for the results of the review. So while me and my research group identified some potential pitfalls and remedies, we received comments from other researchers that it would be helpful to share these and describe the choices we made during the review process so others could learn from them. And in the end, we submitted these recommendations as a communication paper to BMJ Open, where it got published last year. So the first scenario that we discussed in our paper was the choice whether or not to use AI for the title and abstract screening. We read some reviews that had a data set containing no more than 300 papers in total, and they still chose to use AS Review. But we also saw in those papers that the benefit in terms of time saving was minimal. And if you consider the time becoming familiar with the software and also defending your AI related choices in your paper, I think they would all have already finished screening these 300 papers before even starting the screening phase using AI. So when there's not a lot of time to be saved in the first place, I would still recommend applying manual screening. The second issue we came across is that of duplicates in the data set. So the algorithm takes all previously screened records into account when picking the new record, as I told you. And if more and more of the exact same records are labeled relevant, this will probably result in unequal weighing of articles. So normally one would probably already look for a strategy to reduce duplicates before starting screening. But when using AI, this is thus even more relevant. So an important note I want to make here is that not every deduplication software is equally sensitive in identifying duplicates. So you might want to take a look into proper deduplication software. Then a third scenario, so is that the reviewer's choices influence the selection, which is, I think, the big pro of using this, but it also comes with its risks. So if the reviewer makes mistakes or is subjective for whatever reason, the next record that is presented can be the wrong one. And one should think about how to assure reliability of the reviewer's decisions, and therefore also of the articles that are seen and assessed. Our approach included checking the choices of the first reviewer by a second reviewer. And we evaluated those choices for inter-reviewer agreements. But there are also alternatives like performing the screening with two reviewers independently, and then double check with each other for disagreements and articles that are seen by only one of the two reviewers to, well, to receive sort of agreement in another way. So the fourth scenario that we identified is that the screening is stopped either too early, so then you will miss a lot of articles, or too late, and then you are, well, screening through a lot of irrelevant articles and being inefficient or less efficient than you would want to. So, and screening just in time, so exactly after your less relevant articles, found that's impossible. So you would want to, a stopping rule that is at least data driven, which means you predefine a certain number of consecutive irrelevant records upfront, and then while you're screening, you are assuming that you are adding more and more knowledge to the algorithm. So you would assume that it's going to perform better and better over time. And if it keeps pushing forward irrelevant articles to you, then at a certain point you can conclude, okay, probably there's nothing left anymore. So you would do that after a consecutive number of irrelevant records. Yeah, so that's the fourth recommendation. And then we have scenario 5 and 6, and these are more related to each other. That's why they are on the same slide. But we saw that many papers are not reporting all their AI-related choices. And it's, in my opinion, super important to describe all your AI-related choices in the review, or in its supplements, or anywhere accessible, so your screening process is completely transparent. So that's basically the idea of the systematic review. So this means you should inform readers in detail about the search strategy up to the inclusion of articles, so of every choice you make there. And one of the key points of a systematic review is its transparency. So yeah, I think that's an important note to make there. And I think it's also not really rocket science, this recommendation, but we searched for several publications at the time of our at the time of writing our paper, and I could not follow the majority of screening processes of the papers using AsReview. And I think also a large advantage of AsReview over other AI-guided softwares is that it gives the ability to extract the data, and that gives insight into the decisions made. So, but also in which articles remained unseen and thus excluded. But when you are able to extract this data, it's very simple to just publish it aside your review, whether it's via the journal itself or via an data repository. So I would highly recommend to just extract your data and give full insight into all choices made, with regard to prior knowledge, with regard to your stopping rule, but also regarding every article you have not seen. So these were the recommendations described in our paper at BMJ Open. And then I wanted to add a short slide on our experiences. So as you see, we have started at 0. So we had also, I think, a data set of 4,500 articles or so, and we had 142 that were deemed relevant based on title and abstract. And also we reached our stopping criterion, which was 100 consecutive irrelevant articles, after screening 23%. So we also saved about 3/4 of our time during the title and abstract screening phase. So this is, well, yeah, our experience was very positive with this software. There are also some discussion points still, and an example of this is the prior knowledge, so the articles with which the algorithm is trained. It's still a bit vague to me how important this prior knowledge is and how much time should be invested in choosing prior knowledge. And also how many prior knowledge do you then want? Based off the results of the simulation study, it actually does not seem to matter that much. Another point is also the stopping rule. So to define the perfect stopping rule, you should ideally know everything about your data set, but that's the thing, you don't. So that's also when are you safe? And a recent published study from Boetje and Van der Schoot presented an accessible method for the applied researcher to define a good stopping rule. It's also called the SAFE method. And this is an approach switching machine learning models, exhausting model settings to identify every relevant article. So that's very recommended to read. The final point, which I think is important to mention, is that I believe researchers are best helped by review guidelines, how to implement AI using a sound methodology. And I express my hope that review authorities such as Prisma or Cochrane will be jumping in to guide us on this path towards accurate, efficient, and more fun ways to conduct a systematic review. So hopefully, and the next PhD student does not have to screen through those thousands of articles, but can finish, well, a bit sooner. I think that was it.
Excellent. Thank you, Sanne. Does anyone have any questions? Just checking. So please raise your hand if you have any, or put it in the chat. Oh, there's one in the chat, I think. So Ian asked, really interesting presentation, thank you. Do you see a role for the use of multiple AI models to screen the same data set with a similar rationale to the use of 2 human reviewers?
Well, so you mean that you have, for example, one reviewer using a certain model and the other reviewer using another model, so that you.
Well, I guess
duplicate
so.
the
So you kind of
screening that
touched
way?
upon it. I think this is my interpretation of the question, that you were saying, you know, you don't know the priors and how important it is.
Mhm.
So if you use 2 different AI models to screen papers to see how important the priors are, and I guess, you know, to kind of have that thing as 2 reviewers say, well, how much do these underlying assumptions matter in what's found?
Mm-hmm. Yeah, I think it can certainly be helpful. I personally have no recommendations to make regarding what model settings to choose, etc. So therefore, you must really dive into the papers with more technological details about the model. But I think yes, that would certainly maybe strengthen the screening process in the sense of quality.
Right, thank you.
Yeah.
Are there any other questions? Or does anyone have thought of any other questions for Robert? Because I see we have about 3 minutes. No. Okay, well, I guess then I'm just going to say thank you both to Robert and Sanne for really interesting presentations.
Yeah.
And thank you everyone for coming, and sorry again about the confusion with the time. Okay, excellent. Well, bye everyone.
Goodbye.